Okay, if you're a distance learner, you're probably going to want to print this off so that you can write on it and do the same things that we're doing in class. So, last time we talked about and were introduced to logarithms. And one of the most important things about logarithms is that they are related to exponents. So we can rearrange an exponent to look like a log and vice versa. We can take a log and rearrange it as an exponent. The reason that we can do this is because logarithms and exponents are inverses of each other. So just like addition and subtraction are inverses and multiplication and division are inverses, logarithms and exponentials are inverses. So last time we learned what a logarithm is, and today we are talking about what does a logarithm look like if we graphed it. So what does a logarithmic function look like? So at the top, we start with that really important property that we learned last time, which is exponential and logarithmic functions are inverses. And that does show up on your quiz today. So you have one specific question that says, what is the relationship between logs and inverse, or logs and exponents? And they want you to identify that they're inverses. So remember, when we were talking about how to find inverse functions, all we had to do was switch or flip, whichever way you like to think about it, the x and y values. So in our special equations unit, the last set of equations we learned to solve were inverses. And we would literally take the x and y value and switch it, or take the x and y variable and switch them. So to show you how to graph a logarithmic function, we do that by comparing it to an exponential function. So you have three exponentials here, and they go in the order that you see them on your paper. So the darkest one is this top one, y equals 5 to the x. And then the middle one is your natural exponent. And then the last one is your basic. It's the one that we base everything off of, 2 to the x. So this dark one that you see the points on match what's in this table. So for this first point, 0, 1, if we wanted to know what he would look like as a log, all you have to do is switch those values. So instead of 0, 1, we would have 1, 0. And it is very close to the other point on the graph. So this first one is the exponent. This second one is the logarithm. You can do the same with 1 and 5. So 1, 5 becomes the point 5, 1. And lastly, the point 1.5, 11 becomes the point 11, 1.5. So two things are happening here. There are two purposes to this graph. Number one, it's to show you what does a logarithmic function look like, but then the other thing is to give you a visual representation of how they are inverses. So when we're talking about logs, we're talking about these kinds of graphs. So they start out very steep and they're increasing, and then they flatten out and become way less steep. So that's the opposite of what you see here, or the inverse of what you see here. It starts flat and then explodes. Here, it's coming out of that explosion and flattens. Does this make a little bit of sense? You're sure? So we are focused on these graphs. We just have these graphs up here to show the relationship between the two. So we're talking about these guys. Now let's label them what they really are so that we know what a logarithmic function looks like. This bottom one is y equals log base 5 of x. And I know that because of last time. If I have the exponent 5 to the x, when I rewrite that as a log, it becomes log base 5. The one in the middle, he is the inverse of the natural base. So that means that he's the natural log. So he's y equals ln of x. Remember, that's ln, not in. So if you have the natural base, the inverse is the natural log. And then lastly, this top one is just log base 2 of x. How do I know that? Because in the exponent, the base is 2. So this becomes log base 2 of x. So remember, as we move through these, we only care about these functions. These guys are just here for comparison. These are the ones that we really care about. Just like with other functions, we can transform the parent function of a log. So this guy is our parent function. It's just log x. And we can do the transformations that we're used to. So we can reflect, we can stretch or shrink, we can shift left, right, up, or down. We just have to make sure that we know where in the equation each transformation is. So in order to investigate that, we're going to go through this paper. And this paper is probably what you're going to refer to on your quiz more than this table here. So our first one, like I said, is our parent function. And one thing to notice here is that this point is 1, 0. So on our parent function, we have an x-intercept of 1, 0. So what we're comparing that to is an x minus 5. But notice he's trapped in there with the x. So these parentheses tell us that's trapped in there with the x. Nope. Consequences of being late. So this one is 1, 0. This one is 6, 0. And I know that just by looking at the graph. So this one is 1, 0. And now this point has been shifted to the right by 6, 0. Or 2. I shouldn't say by, I should say 2. In this one, instead of a minus 5, I have a plus 5. And notice where his intercept has been shifted to. He's at 0, negative 4. So from these two things, I can see that when it's trapped inside with the x, you're either shifting left or right. So in this case, you shifted right by 5 because you started at 1 and you ended at 6. So that means you shifted right by 5. On this one, you shifted left also by 5. So you started at +1, and if you shift to the left by 5, you end up at -4. So then this reminds me, if it's trapped inside with the x, if the plus or minus is trapped with the x, you use the opposite of what you see. So if you see a +4, you do -4. And if you see a +5, you do -5. Does that make a little bit of sense? Are you sure? Okay, so now on the next ones, it's outside of the log. So this one, it's trapped inside with the x. This one, you're adding and subtracting to the entire function. So here's your parent with that same x-intercept at 1, 0. And when I added 5, that point shifted up to 1, 5. And when I subtracted 5, it shifted down to 1, -5. So that transformation is direct. You don't use the opposite. If you see a +5, that means you took your whole function and moved it up by 5. So this one is a shift up by 5. This one is a shift down by 5. And these are the same rules from any function that we've talked about so far this year. If your number is trapped in with the x, you're moving left or right. If it's outside of the x and being added or subtracted to the entire function, it's an up or down shift. So then the next easiest is the reflections, and that's on the back page. So if you flip it over, we're going to look at the last set of functions. So the first one is the one that we're used to. This is your parent. This is a horizontal reflection. So the first one with the negative on the outside is a horizontal reflection. I'm going to highlight where that negative is because it matters. This is the reflection that we're used to. So we're used to seeing a function and flipping it horizontally like this. So that's when we took our smiley face parabola and flipped it down to a frowny face. When you have a horizontal reflection, you're flipping horizontally. The fancy words for that is you're flipping across the x-axis. So I'm flipping across the x. This is your x. But if that negative is trapped in with the y, now trapped in with the x, now you're flipping the other way. So instead of going from down to up, this time I'm flipping it vertically over the y-axis. So this second one is a vertical reflection. The first one is horizontal. The second one is vertical. So this one would be across the y-axis, and we refer to that as a vertical reflection. And what you really want to pay attention to is where the negative is. If it's outside, it's x-axis. If it's inside, it's y-axis. So this guy is new. This flipping across the y is new. Okay, so then the next two are not my favorite, but we're going to do them anyways. So we've talked about left, right, up, down, reflecting. So the only thing that's left is stretching or shrinking. And this time we can stretch and shrink in two different ways. So let's look at the one that we are used to. That is above our reflection. We're used to this guy. So the thing to notice here is that it's outside of the x. It's on the front of the function. So his position matters. The stretch or shrink is on the front of the function. If it's a whole number, it's a stretch. And if it's a fraction, it's a shrink. And hopefully we're remembering this first one's a stretch by 5. And the second one's a shrink by 1/5. But we have a new element to add in. So they call this, when it's outside the front of your function, these are horizontal stretches and shrinks. So the first one is a horizontal stretch. The second one is a horizontal shrink. And here's what they mean by that. They're saying that when you have 5 on the outside of your log, you are stretching away from the x-axis. So you're basing where it's going off of the x-axis. And this one, they're saying you take this original function and you shrink it down toward the x-axis. That's why it's a horizontal stretch or shrink, because you're doing it in relation to the x-axis. However, if the number is on the inside and it's on the front of your x, so he's on the front of your x, this is a vertical stretch or shrink. So I'm going to just highlight him. If the number is in front of the x, so last time it was in front of the log or the natural log. This time it's in front of the x. This is a vertical stretch by 100. And this guy is a vertical shrink by 1/5. The reason that they call it vertical is because you're either stretching it up toward the y-axis or you're stretching it down away from the y. Or you can think about it as getting higher, like this might be an easier way to think about it. This guy looks like he is going up, and this guy has definitely gone down. Like if you compare him to this one looks like he's been stretched up, and this one has been stretched down or shrunk down. You won't ever be like asked to identify which one's vertical. Like I won't give you a graph and say which one's vertical and which one's horizontal. What you want to pay attention to is the position of the number. So if it's inside, it's vertical. If it's outside, it's what we're used to and it's horizontal. And you'll have this to refer to while you do your quiz. So this paper is a visual representation of this table. This table just gives you like the vocab for each transformation. So the first one is the first one that I have here. And they call this a, what do they call it? Horizontal translation. Those are the fancy words. A horizontal translation, but really we know that that's just we moved our graph left or right. And notice it's showing you here that it's trapped in with the x, and then it gives you some actual examples of what it would look like. The next one is a vertical translation, which is just fancy for shift up or down. He's being added or subtracted to the entire function, and then once again it gives you some actual examples of that. Okay, next one is just a reflection. But we need to label these two in case you guys want to use this. So if it's on the front, it's horizontal. It's the one that we're used to. If it's inside, it's vertical. Remember, this one's x-axis, this one's y-axis. The next one is a vertical stretch or shrink. It says that it's going toward or shrinking away from the y-axis, so I know it's vertical. And lastly, we have a horizontal stretch or shrink. So this table is the math symbols. The graphs is a visual of what is actually happening with your logarithmic function. So we're going to use, I use this one the most, but you're either going to use this one or this one to, 1, describe transformations, and then 2, write the function given transformations. So let's look at page 85. We are not doing 2, 3, and 6. We are only focusing on the logarithms. Okay. So first one is log base 2. We don't do anything with that base 2. The base 2 is not a transformation. It's just telling you which log we have. So this is a log base 2. This is your original. So we took that original and added 4 to x. So he's trapped inside the x, which means we went left 4. That's the only thing we did to this log base 2. We took the entire function and shifted him or translated him to the left. Remember, when he's trapped, you have to do the opposite. And you may want to somehow make a note to yourself that these parentheses are important, especially when you're writing your own functions. Okay, next up, our original function is log with the natural base, so ln. Remember, that's ln, not in. This time, we've done 2 things. So we've reflected inside with the x, and then did some kind of shrink inside with the x. So I'm going to write those down. I know that I reflected, and I know that I had a shrink. But what kind were they? So that's where I use this paper. I find, okay, what is it when it's on the inside? Okay, that's vertical, so I reflect it across the y-axis. And then I go to my stretches and shrinks and find the one where the number is next to the x. That is a vertical shrink by 1/2. So I took my natural log, I reflected him across the y, and then I shrunk him down away from the y-axis by a factor of 1/2. Are you hanging in? Okay, I would write this down as a reminder. It's probably going to be hard by the time that you get there, but when you're writing these, there's two things. Number one, this. So on the assignment, you have one similar to this, and a lot of people are writing it like this. They're doing this as their shrink and this as their reflection, and that's not right because that looks like 1/2 minus x. You will never have anything like that. A natural log, a logarithm would never be written that way. You're okay there? Then the other thing is this. You don't want to write your reflection just like this, because what this looks like is log subtract x. The way that you would read that is log minus x, when really you're reflecting. So you need to make sure you always put those parentheses around. Is that making sense what's happening there? Are you sure? Oscar, are you alive?
Yes, I am trying to.
Okay. Last one of these. We did two things to this. Now remember, that little 1/4 is just the base. It's just telling us what kind of log we have. So you write down what two things happen to this function. Go. I'll come through and make sure. See what's up. About 30 seconds. If you're just sitting doing nothing, you're like 2 of everybody in here, 2 out of 17 kids. So maybe ask a question. Or, actually try. Maybe we should just do this thing where you can't leave early unless you actually write crap down. Stuff down, I shouldn't say crap. Stuff down. Because, why you get to leave early if you're just sitting there doing nothing? Okay, this 4 on the front of the x is a stretch. So I have to remind myself he's a vertical stretch by 4 and then down 5. Because you're taking this entire function and shifting the whole thing down by 5. Okay, the last part is writing your function. So in the quiz, I gave you your transformations in the order that you would write them in the function. So I'm going to read these slightly differently. I'm going to read them like they would be in your quiz. So we are taking log base 1/3 of x, but we got to rename them. We can't call them f of x, so let's call them g of x. And the first thing that we're going to do is a vertical stretch by a factor of 2. So if it's vertical, that means it goes inside with the x. Okay, so I'm going to do log base 1/3, and I put my stretch 2 in front of the x. Then it says translate 2 units up. So I'm going to add 2 on the end. To make this look even better, you could put parentheses around the 2x. You don't have to, but you could. The next one, they want us to translate the natural log. Once again, I'm going to read it in the order you would get it on your quiz, because the quiz does it a little bit easier. So the first thing we look at is this horizontal stretch by 8. So I'm going to go to my paper and I'm just going to verify when I have a horizontal stretch, that number is on the front of my log. So I'm going to say 8LN. So I just did this guy, horizontal stretch. Then it tells me I'm going to go 3 units right and 1 unit up. Okay, 3 units right is going to have to look like x minus 3, and you must have the parentheses. The parentheses are required in this one, because then they want you to shift up, and we need to know which one is the horizontal, which one is the vertical, and we only know that if you guys put parentheses. Okay, last one that you're trying. Oh, don't name it F. It's got to have a different name. G. You try 9. The only thing you're doing is reflecting and then going down by 9. So see if you know, where do I put that negative? Where do I put the 9? Oh, I can see lots of you guys want to be able to leave early. Now everybody's writing stuff down. I accept. Good job.
How would you know if it's vertical or horizontal though?
What do you mean?
Like, you know how it asks for reflection?
Yeah.
How would you know if it's vertical or horizontal?
Because it says reflect in the x-axis. So you come to your paper, and I have here x-axis would be a horizontal reflection. Does that help?
Yeah.
Let's go about 20. Ten. 3. Do-si-do. Okay. Reflect across the x is a negative on the outside. We say log base 5 of x, plus 9. So he's trapped in with the x. Is that true? Yes. So I think at this point you won't know what questions you have until you try the quiz. So let's have you guys try it, and then I'll be walking around and just stop me if you have questions. Yeah? Okay.